Okay, hello and welcome to episode 33 of Codebase Alpha. It's 9 in the evening here in the UK. Hope it's good where you are. So today we're going to revisit Parsers and the F-sharp work we did back in episode 27. And joining me again is Mårten Rånge. So we'll just pop over into the pair programming screen and have a look at what the code we wrote last time and give a quick recap. So here we are in the code. So welcome, Mårten. Welcome to the stream. Thank you for joining me again.
Yeah, hello there. It's nice being here again. Yeah, it was fun last time and maybe a little bit challenging.
Yes, a bit challenging.
And I actually, several of my co-workers were watching this the YouTube video and they liked it. So I think we managed to. Well, let's not pat our back too much on the back, but I think it was a good show. I think.
Oh, I think it was interesting. It was different and say a different level of challenge perhaps to the usual kind of shows that I do. So, Cody Beer, welcome to the stream.
So, have you been thinking about what we did last time?
Yeah. So, if we look at the screen, what I did about a week ago, and this is well after we'd finished the stream, I went through and just tried to kind of annotate some of the blocks of code that we wrote with some comments. And in most places I was fairly confident that I understood what we did, and there was a few kind of questions. But I think if we should do a quick recap, I guess, of where we got. I think the best place to start, perhaps, is with the very first thing that you wrote, which was the type definition for parser of T.
Yeah.
Perhaps you could just talk us through that and just remind us what that was all about.
Yeah. So I think that's a good start. I think so. Like we discussed briefly, I think one of the differences between maybe an object-oriented framework and the functional framework is that in an object-oriented framework we start with the big picture and we decompose it perhaps. But I think with a functional framework, often you end up starting with the smallest unit, kind of atom that cannot be divided any further, maybe. And from that you build functions that compose on that thing and build up kind of a giant. I use the word molecules, and in this case, this is the parser function, and this is a suggestion. So what this type definition is telling us that in our case, a parser atom or a parser function is a string, a function that is given a string and an integer produces an option value of t and an integer. The string in this case is the input string. Like we want to parse a string value. The integer here is the position, the current position in the string, and this will change. So what we could have used here were maybe spans that are new in .NET, but I don't really know how they interact with closures. And what we produce now is what the parser produces is an optional value where it's like, let's say we want an int parser. Now, then the parser given a string and an int will produce an answer saying, yes, I was able to parse this. Here's the result, the integer. But it also gives us the new position directly after the integer in this case. And that will allow us to continues to sort of combine parsers together, because a parser like that tries to parse an expression like 1 plus 2, if you see it on the screen here. If the int parser will succeed parsing 1, and then we need another parser to parse the plus sign, and finally we apply the int parser again. And this int here at the end will allow another parser to take over when the int parser no longer can parse something successfully, if that makes sense.
I think that's actually the fundamental thing, isn't it? Is that we've defined a parser which parses kind of one thing, haven't we? So if it's an integer parse, it's just going to parse the integer part. So we need to combine them some way. I'm Geek. Welcome to the stream. Thank you for joining us. So that's why I guess one of the other titles of the stream was Parser Combinators. We're actually going to be building up, as you say. This is the definition of and it's one of, I guess, many possible definitions we could have come up with for parser. But this next piece of code, the p-char, is your atomic parser, isn't it? This is what will parse a single character. It actually implements what you said the type does. It consumes the string and the position, which is strut and pos. It does this test, which is, as you quite rightly pointed out last time, is the only time we ever do that test. Are we in the string or not? And then it returns whatever was at that position and increments the position. And that's exactly what you said that type does. So that's really the fundamental, the atomic operation, isn't it? Is read a character, spit out that character, and increment the pointer. So the other thing that we need to kind of talk about, I guess, is this p of. And we're using this shorthand here for p, type p.
Oh yeah. Yeah. So that might be a little bit weird. So we're using what is called here a single. I think it's called a single union case. So if you go up to the definition here, so the parser says p of something, and usually when we define a union case or a union class in F#, we write something like this, and we have several cases. Like that. And that's good, but it actually turns out that it is actually useful to have a single case as well, because that kind of and one way that some people uses the single case single case in union in F# is like, say we want to have typed strings.
Yeah.
So let's say if we have the address, which is a string, then we could say, well, that is an address of string. And now we have, instead of sending a string to a function, we can send this address type, which contains a string.
Yeah.
And that allows us to sort of creating typed strings.
Yeah, strongly typed strings. Yes, it's a really interesting concept. This is where the domain-driven design comes, isn't it? You're taking aspects of your domain and you're giving them type names.
Yeah. And of course we can do this in C# or any other language, but the benefit here in F# is that it's so easy to create these types. There are like no reasons not to do it, kind of.
Yeah.
Because if we had to create a class and a struct, and we had to store it in a value, and we had to do the constructor, you get bored by that.
A lot of ceremony around building that kind of idea, isn't there? Here it's just the word of, really, isn't it?
Yes. So and you might heard the name. Sorry, now I'm going to digress a little bit, but you heard the name of algebraic types, or ADTs.
Yes.
And that is very powerful, because what we ever have, usually when we think about algebra, we think like these things. 1 + 2 × 3, that's kind of an algebra when we put things together. But with union types, we have algebra. So, well, if we make my option in this case, and then I make this, just as an example, my sum of t, my none. So this is kind of meaningless type, but I didn't come up with a better one, right?
Yeah.
This can be seen as this comes called an add operations or a union operation, and that kind of is an algebra.
Yeah.
Sort of like if you can compare it with this operator in some sense. And then what you also have is this other thing in algebra where we can say we multiply by integer and so on and so forth. And this is an algebra of creating types. And because it's so short, and I think especially with domain-driven design, it's so easy for us to model succinctly domains in types in F#. And I actually found that when I was working at Ericsson, we were actually able to sort of model a particular domain in F# types in such a way that the domain expert were able to read and understand the domain in F#, even though that person knew nothing about F#. But it was understandable.
Yeah.
But that is a diversion. But I love algebraic types. Algebraic type, the name kind of scares you, but it's so good.
Yeah. Okay, so we've got our basic kind of single character parser. We created then this helper function just to kind of allow us to start off running a parser, so that's okay. And then we started to come up with some more kind of complicated functions that we started to build, which were building towards a computation expression, which comes a bit later. So maybe you could kind of talk us through some of these, what we did here.
Yeah, so kind of talk about algebra. We are trying to define kind of algebra of parsers as well, in some sense.
Yeah.
And we need ways to put parsers together to create bigger and bigger parsers. And we started by creating this p-return parser and p-fail parser, which kind of seem meaningless, but they are parsers that always either succeed with a particular value or fail.
Yeah.
At all times. And this is powerful when we start using the bind parser further down, where the bind parser is a way to sort of chain parsers together in a flexible manner.
Yeah, so this was a kind of bit of a light bulb moment for me, because you wrote bind, and I've heard of bind before, but it's never been really that clear about what its function is, because it's couched in it's couched in this kind of definition here. This definition, as you say, is kind of almost it's one that you learn. You just know after a while with working with functional programming this kind of form on screen here. But it's a pattern, yes, and you just know it, and you use it without thinking, just like you'd use, I don't know, decorate pattern or whatever. Upgrading Dave, welcome to the stream. Good to see you. But I kind of after the stream and about 10 days later, I was kind of sitting there staring at it, and I was flicking through F# for Fun and Profit, and they talked about this railway-oriented programming, which is not necessarily exactly what I was interested in looking at. But I saw this diagram that's on screen at the moment. I'm using CodeRush here to embed images into the comments. So and this is pretty much what we're doing with bind. We have a function which is our parser, which accepts a string in a position, and it either succeeds, in which case it produces this sum, or it fails and it produces none. So this is like a wrapped value, isn't it? It's an option. It's not a string in a position. So you can't then feed these values directly into the next parser in the chain.
Yes.
So
and he has very good pictures. Like you have two tracks here.
Yeah.
You have the good track and the bad track. And as soon as we get into the bad track, we kind of bail out.
Yeah.
You could almost see it as an exception, but not really. And we are creating kind of functions that are a little bit like the tracks that operate on these good and bad values. And something that is different here, if you normally write this parser code, is that if you write it kind of in an imperative way, you always have to sort of deal with the bad track. Like, if this failed, then do this. If this failed, then do this. If this failed. So you're filling the code with the bad path, and you're kind of masking the good path. And I think one of the very powerful things with the railway-oriented programming is that what you're looking at is the good path, and the bad path is invisible.
Yeah.
And I think that's quite powerful. And this is very much railway-oriented programming, I would say, what we're doing here with parsers. But we're not combining values, we're actually combining functions.
Yes, absolutely.
Which is more powerful than combining values
Yeah.
and more mind melting when you're thinking.
Yeah. So I've tried to explain. So if folks do go to GitHub and clone the repository, and I'll put the GitHub in the chat, then I have all this is on GitHub, and we'll continue to try and comment this code to try so that people who do download it and have a look at it and have a play with Parsers, which I do hope you all do, and try and get some idea about what this code is doing after the stream's finished, because it's all very well understand it while we're talking and Mårten's here explaining stuff, but now I'm not saying that the comments I've made here are actually 100% correct. They're just my interpretation or my notes. But you know, we could have the Discord for any questions that people might have. So I'll just pop the Discord invite into chat as well. So do feel free to join the Discord, and there's a functional programming channel in there which you can ask questions or comments or whatever in there. And if you have anything that you'd like to know more about that comes out of these F# streams, but so that's F bind. So F bind, I'm pretty solid with F bind. Yes. And then we come to F combine, which sounds a bit like F bind, doesn't it? It's another combiner.
Yes. So what we do then when we define this p bind function is we start defining other things using p bind.
Yeah.
Because it's such a flexible manner, and I was thinking that we could probably maybe even define many using that, but I'm not sure. Well, I didn't come up with a good way to do it. But p-bind is so powerful, so we can actually build a lot of other parsers using it, and p-combine is one of them. And maybe what's confusing with p-bind here is that the types we haven't written. So I'm going to write out the types here, and maybe that makes more sense to people. So what is the purpose of p combine? And the purpose of combine is to combine two parsers and throw away the result of the t parser. So if you see the types here, the u parser is a parser of u, the t parser is a parser of t, and the final result of this thing is a parser of u, which means that we only keep the value of parser u.
Yes.
The parser t is kind of thrown away. And then you might think, why would this ever be useful? But it is very useful when it comes to parser, because we look for a specific character to see if this is like a plus sign or a minus sign, to see if this is a particular operator. But we don't really care about the value, but we might care what comes directly after it.
Yeah.
And this is just we can implement that using p-bind, but this is just a convenient wrapper around this thing. And I'm going to introduce another name here now for this, and this is called keep right. And this is one thing that is a little bit confusing because you might think, well, we're actually we're actually keeping the left here, and that is true. But the reason, and I think this is kind of a problem sometimes with F#, but the reason we call it this is when we write the parser like this, and we're using this thing here.
Yeah.
Now I think it makes more sense.
Yeah, because the t gets inserted to the right of the u, doesn't it? In
yes.
terms of the position of the arguments. Yeah.
Yeah. So it's kind of is weird, and we can see that in the other places in F# when you're writing like append, and what happens is actually that the first argument is append after the second, which is like weird. But the reason for that is when we're writing using this shove syntax to make it work. If that makes sense.
Absolutely, to you. Yeah. So I'm fairly used to the concept with what we call in the shove character is the triangle there. It's actually the pipe, but on Gareth Hubble's stream we started calling it the shove into, didn't we? So yeah, and the T here takes the place of the second argument. So it'd be, in theory, this could also be written as that, couldn't it?
Yeah.
Yeah.
And then it makes no sense.
It doesn't make any sense then, yeah.
Yeah. So I want to define now, just to, as a simple getting started, right? Do you want to make a try to this on how to do it, or should I?
Yeah, you carry on.
I want to define the keep left parser.
Okay.
And this is the reverse of the keep right, or the inverse, or whatever we call it. So with the keep left parser, we want to return the result of the first parser. We want to run both the parsers, but just return the result of the t parser.
Yeah.
So how do you do that? And we will come back to this, and they will prove useful. Now, in this case, we're running the t parser, and this is the t value that we want to preserve. And then we want to run the u parser, but we don't want to return the value of this thing. And the way we do it here, or one way to do it, there are many ways to do this thing, is that we
ignore it, yeah.
We write p bind again, and now I'm going to switch row because the row got a little too long.
Yeah.
And here we have a u value, but we don't care about that one. And then we go p return tv.
All right.
So the way to read this, we first run t parser, and then we bind it together, and then we get the t value.
Pass
and
that in, yeah.
That is what we care about. But we also want to run the u parser because we want to sort of read the value and then read something that follows that value. But we don't care about that value particularly. And in order to sort of do that, we sort of bind again together, and we discard the u value because we don't care about it, and we return the t value.
So this p return is almost like the terminator of this process, isn't it? So it's just throwing back rather than returning the u parser. We're actually going to return the value of t.
Yeah. And so the way p bind works is that this function here is supposed to return a parser.
And p return is a parser, isn't it?
Yeah.
Parser which returns the value.
P return, and the value becomes a parser that always succeeds with that value.
Yeah, and
so that makes that useless function useful.
So that's this function. Where has it gone? This function here, p return. Let me just go up. Yeah, p return, where we don't care about. It takes a value. We don't care about what the string is. We just return the value, and the same position is unaltered. So we throw that way as well. Yeah.
So this is just to sort of wrap a value in a parser.
Yeah.
And fail is the opposite, or the symmetric, whatever we're going to do, where it's like, we're just going to fail whatever it is.
Yeah.
And we used that when we implemented the satisfy parser. I think I don't remember where I did it. The satisfy. I scroll down here now. I hope you can see it.
Yep.
And satisfy. If we succeed, we return the character. Otherwise, we bail out. We fail, and we fail with the fail parser.
Yeah.
So these useless functions are actually useful.
Yeah, I think the important thing here is we're in the world of parsers, aren't we? So we're not actually dealing with characters when we're talking about all this. We're actually combining parsers, and those parsers may result in a character being spat out, but actually it's just the way we define the parser.
Yeah, and that's also a big difference between. There are some symmetries here or some similarities between this and regular expression, right?
Yes.
Our regular expression, in some sense, is a parser combinator too. But the big benefit of how to do parsers this way is you actually get out actual type. You don't get out when you parse something, you use regular expression. You get out groups of strings that you need to parse again.
Yeah.
Often.
I think that's a really interesting point, because one of the things I did was when I was going through this, I would just hover over some of these things. So here, I'll hover over p many. If I can just have focus for a second. If I hover over p many, F# will tell me the type of that, and p many is it takes a parser of t and it turns a parser of a list of t. So if it's a parser of character, it's going to come back with a list of characters. If it's a parser of int, it's going to come back with a list of ints.
Yes.
This is really interesting, especially when you come down here and we look at something like pint. So pint we've built up.
I'm going to scroll down to pint, right?
Yes. So pint is here. If we hover over this, it's actually a parser of type int.
Yes.
Just because of the definition of chaining these functions together, it's actually worked out for us the type of that, and that's now a strongly typed parser of integer.
Yes. Yes, and that's one of the, I think, benefits of doing it this way, is that we're actually producing the actual value. And I hope that we get to the point today that we will produce, we will parse an expression like 1 + 2 something else, right?
Yeah.
And then what we will get out is actually an expression tree. That is what we get out. And then using that expression tree, we then can loop over this expression tree and perform operations on it.
Yeah.
So that's what we're going to get out.
Okay.
So one thing I wanted to do here, and I have, I think, good reasons to do it, but it might be a little bit strange. So to get started here, I want to introduce some common operators used with parser combinators.
Okay.
That will help us later to understand fparsec one. So that is something I want to do, and operator overloading is a topic which is create heated discussions.
Right.
And I'm not taking stands there, but what I'm saying is that if you want to take the knowledge here and use the fparsec, you will be exposed to certain operators, and I'm going to make the operators here the same as fparsec, and they make sense,
right,
when you learn, because there is there is sense to these things, so they can be useful to learn just from that thing. So let's see where we should end. Shall we? If I move up the cursor here.
Yeah.
And the different ways to declare, you've probably seen this way to sort of, define operators in F sharp like this, something like that.
Yeah.
Now the drawback with this way to do it, and this is why I try to avoid doing this, is now this becomes a part operating in a global scope, and that pollutes the global scope. What I want to have is an operator just for the parser.
Right.
So
okay.
we don't pollute the scope. And the way I usually do it is how you declare. Now this is a kind of little complex way, but this is how we can declare extension methods in F sharp. But here I'm going to extend the parser with some more methods, and with some more methods, or more specifically, some operators.
Okay.
So what we say here basically is what we say here is like we have the type parser t, and we extend it with a few more methods. And one of the most common ones is which you very often see when talking about function programming, is this operator, which is an alias for pbind.
And it's actually wonderful in that the ligature that's come up from Fira code here is actually showing 2 tracks going into one, isn't it?
Yeah. Yes.
I don't know if you can see. Can you see that how that's? I don't know if you're using Fira code your end, but it's.
No, but I see it on the stream.
It's quite wonderful that. So it's actually illustrating what bind is doing. It's quite nice.
Yeah. And so this enables us, when we write, instead of writing pbind, we can now write, using this thing here, we can now start writing, if you have parsers like, I'm just going to sort of do t bind fun tv p return TV, something like that.
Yeah.
Now this is not a parser, so it won't work. But if I type pchar, that should work, right?
Yeah.
No? And so that's one way to do it. And this is a very common operator in function programming. And if you look at Haskell, this is their logo.
Oh, is it?
Haskell.
Right, okay.
Yeah. So it's super important for them, you could say. And this is the kind of for barriers. It's very, very good to scope operators to types. In order, there is another way to do it, which is complicated. But sometimes you have to do that. But in this case, this works, and I think this is preferable. Another very common operator. Now, if you remember, we talked about this keep right and keep left.
Yeah.
Now we're getting to how it looks in fparsec. So I'm going to define the keep right one. And I don't know why it's complaining. Oh yeah.
It's just spelling, it's just spelling, isn't it? What's it say?
It's just that it's a little bit inconsistent here. So
okay.
Now so what this thing now it's sort of keep the right.
And the
right
and the dots on the right, yeah.
Yes, that's exactly how you should read it. So if you do it this way, now we are parsing the character on the here, but we're throwing away that result. We don't care about that result. And then we parse this character, and this is the result we keep.
Yeah.
So you read the dot as which side do we want to keep. So in my head, these operators make sense.
Yes.
But you kind of need someone to explain them a little bit.
Yeah, I think that's it. When you first see them cold, you just think, "What? Someone's making up this," and it's really complicated. But
yeah, if you see it code, then we do the same thing for keep left. So now what we're doing is we're parsing this character, we're parsing the second character, we throw away the second character and keep the first one.
The first one, yeah.
Another very common operator that you will see is this operator here. Typed the wrong thing here. Map. And that is the pmap tm. Well, pmap, is that not defined here?
That should be. I think it might be below. Yeah, yes. Pmap's here, yeah.
So I'm going to move it up then.
Yeah.
Yeah, just to sort of make it see if that thing works. Seems to compile.
Yeah, fine now.
And that will allow us to sort of type things like what is it complaining about? Let's see if I did it correctly. Mapping function. No. I flipped it. This is easy too.
Yeah.
So what this thing does is it reads the character and then it maps the character into a string. So we could have written this as pmap instead.
Yes.
Right?
Yes.
But this is when you look at fparser code, this is very, very common.
Right.
So I just want to introduce them as sort of aliases.
Yep, that's good.
Now, in addition, I want to do a pair parser, because we're going to maybe use that later on. This is also common. So sometimes you want to keep both sides. And then we need something which is called ppair, which then reads both values and return them as a pair.
Okay.
And here I'm thinking maybe you want to implement that.
Oh, yeah.
You can use this parser syntax up here.
So we're going to take Fabarius. Thank you for the follow. So U parser and a T parser.
Yes.
And that's going to give us So we're going to use this parser, the computation expression form of this. Okay, so we want to keep both of them. So let's have a look what we did before.
If you look at the PMap, what you do is you just run the T parser.
Yeah, and then we want to run.
And then you run U parser, and we return that as a.
So first equals T parser.
Yeah, that's good.
Let bang second equal U parser.
Yeah.
And then we want to return, I guess first second, is it? First comma second. Is it something like that?
It looks good to me.
Okay. Wow, I've written some F sharp, folks. Maybe I'm starting to understand this.
Getting started. And now this thing works, and this now will allow us, if I scroll down to our example below, now we can write
okay, right,
P char, and this allows us to read 2 characters and keep both of them.
Yeah.
Now there's another one I want to introduce, because when we're going to get more advanced today, we're going to run into the situation that we want to run that we want to sort of run test to run a parser.
Okay.
And if that thing fails, we want to run another parser. And that is used for like test if this is a just to give an example. In regular expression, you would type this as slash. No, I had to press wrong. Sorry, that was not my intended intention. I don't know what happened there.
No,
sorry.
Don't worry.
I pressed a few buttons and that happened.
It's just the weirdness of live share sometimes.
Okay, I want to have a backslash. I'm failing with that thing.
Okay.
Give me a backslash.
Whoops. There you go.
Yeah. And then we go. In regular expression, we type something like this, right?
Yeah.
We want to have the case where we try first with a digit, and if that fails, tries as
white space. Yeah.
Yeah, and that's what we want to define now. So, and I would say we can call this P or else. U parser, T parser. So this parser, we cannot really implement using. We have to go back to basics to do this.
Okay.
So we have to define it using this thing here. So what we're going to do here is and this is a trick we used last time to sort of we pattern match, because we pattern match out so we get the function. So you remember we have this as single union case.
Yes.
Of P parser.
Yeah.
And we can pattern match in the argument list. So now the T parser here is actually the function. And U parser is the function. So we have them, they are directly accessible.
Okay.
This is just a trick that is often used when you're using single union case, that you are pattern matching in the function. So how should we implement this thing here, right? What we want to do is we want to run this parser first, and if that succeeds, this is the value we return. Otherwise, we run this parser, because that is what we want to do. We want to run this first, and if that succeeds, use that value. Otherwise, run this thing here.
Okay.
So let's try that again, right? I'm going to let you write a little bit code now.
Okay then, so I'm just going to scroll up a second, because we've got something very similar to this up here. So we've got this where is it? This kind of idea here where we're matching the output of, oops, you're going up, that's it, yeah.
Yeah, you scroll and I follow.
Okay,
now.
there we go. So, where are we? Let's scroll up. So here we're running parser T. with the string and the position, and then we're evaluating. We're doing a match on what the output of that option is. If it's either none or some. So we could do something very similar to this, can't we?
Yeah. It's very similar.
Let's try that. So we were going to
either Draco 401. And I think there was a Rambling Geek as well.
Yes, Rambling Geek's here. Draco, welcome. You record default with in option. Okay, I'm not sure for Boris. I'm still learning here. So hi, Rambling Geek. Hi, Draco.
So you want to run the T-parser here, right?
Yeah, I'm just T-parser. So T-parser, and we're going to take in the string in the position.
Yes.
And that's going to give us back. And we've got two options. So we can either match with some.
Yep.
And that's going to be the syntax is not that memorable for me. So it's going to be a T value and a position. So we're going to get T value and a T position.
Yep.
And if that succeeds, then what we want to do is return that, don't we?
Yeah, just return that value.
Yeah, so let's back up here. So it just looks like we're actually going to we're just going to say T value here.
No, we want to wrap it in sum, right?
We got to wrap it in a sum. That's right. So sum. We're just going to return the same thing, haven't we? Really?
Yes.
So
we actually can match on a non case first.
Yes. Let's just finish this off. So T parser, no, say T val, and it's going to be T pulse. Else, so we can match on none, and if we do match on none, then what we want to do is actually run uparser.
Exactly right.
On the strut and the pos, because it's exactly the same thing.
Yes.
And oops.
And the only thing you missed here is writing with after.
With, yes. Yeah. Okay.
Otherwise, this looks fine to me.
And if we do that, then we then we need to return some. No.
Because uparser returns the value.
Uparser returns the value. So we just want to return.
So you're done.
Okay, so we want to return just uval, is it then?
No. So you run uparser here, right?
Yeah.
And that uparser returns some value.
Yeah.
And now this is the result of this function. So there is no need actually to do anything more than
so
this.
We could just do that.
Yes.
Yeah. Yeah, absolutely. Yes, that's correct, isn't it? Of course it is.
So sometimes it's simpler than you think.
Yeah, you start to overthink it. But yes, you're right. So that's going to already output a sum, isn't it? Or a none if it fails.
I was asking if I'm Norwegian or Swedish. I'm actually a Swedish citizen living in Norway. So I'm a little bit of both. And the arrows are some kind of if statements. Yeah, they are. Yes, like for Barry saying, it's a little bit like switch statement.
Yes.
Like we're matching things.
So this kind of thing, this pattern matching is now in C#. So it's exactly like doing a switch statement. It's the colon, as Fabarius points out. Basically, it's the colon in the switch statement.
And in C# as well, it's also a switch expression these days, which is exactly what it is in C#.
Yeah, it's no longer a statement; it's just an expression. Yes.
So that's good. So now we can define the operator for this thing here. And this is good stuff because we're going to use that more. And I'm just going to define it as it's commonly defined in fparsec.
Oh, right.
TU UT. hopefully I've written this correctly, and then we can write. Now this is kind of silly. It doesn't make a lot of sense, but we're going to try it later. So what this thing does here now is it. I'm going to stop following you. But what I don't know if you see my screen, if I'm correct way.
Yeah, following you.
So what this thing here now does is that we run first the P character parser, and if that fails, we run it again. So that's meaningless.
Yeah.
But imagine it was something like. Now this won't compile, but it could be something like this.
Yeah.
So try first as an int and otherwise. And the reason this doesn't compile is that these types don't add up. Now, to go further now, what we can do now, which I think is interesting, is now we can define a parser that can either parse a variable named or an integer, or an integer, and that's something I think we should try to do.
Yes, that gives us some algebra that we can pass, isn't it?
Yeah. So I'm scrolling down now.
Yeah,
here.
Following you.
Yeah. So the first thing we want to do, in order to sort of capture this, because we need to sort of when we're parsing a variable and an integer, we need a common type for these two.
Yeah.
Because otherwise we cannot run the OR parser on them. Because if we don't have common type, then OR parser requires both sides to be the same type.
Yes.
And what we typically define is we define something called an abstract AST, abstract syntax tree, or an expression.
Okay.
And I'm going to have, so what we ultimately want to sort of support is something like this. So how should an AST look like that? And since this is not an AST, since this stream is writing parsers, not writing the perfect expression trees, I'm going to write a suggestion and we can talk about that. And now we're using union case. So we can call it const of int.
Okay.
So this thing here is then a constant term in our AST. So we will map 1 and 3 to constants.
Yes.
And then we have variable of string.
Yeah.
And that is and that is then like x. And then we need a way to combine these two, and that is sort of
like an operand or something, yeah.
A binary operation, or whatever we'll call it, of AST times AST, and we have a binary op. And a binary op in our case is another sort of a simple case, and that is either add, subtract, multiply, divide, for example.
Okay.
So now this AST now is able to.
Lucky Dora, thank you for the follow. Thank you very much.
Express what we're doing. So how would we express this thing here using AST? Well, we will write our expression something like this: const 1 and binary operation, comma. Let's see if I type something wrong here, and just interrupt me if I go too fast or too slow, whatever.
Don't worry, carry on.
And then we go binary operation again, and then we go variable x, comma, multiply, comma, const 3. Have I put all the parentheses where I should? No, probably not.
Yeah, one more. That's it. I think.
Yeah, it looks like that. So this is, so our hope is when we run the parser is that it will build an expression tree that looks like this.
Okay, and that's something we can evaluate then, isn't it?
Yeah, and that we actually can evaluate. So here, the inside here is because multiply binds stronger than add. The binding operation here is multiply x with 3 first.
Yes.
And then add whatever result from this thing here together with 1.
So our parser is going to have to understand operator precedence here, isn't it?
That is the final goal.
Yeah.
Let's see how far we get.
Yes.
Yeah. But also hopefully we get to the point where we can write parentheses.
Yeah.
But this AST will be able to handle that as well. So this AST kind of works for that. So when we have this thing now, what we can do is we can write a parser that can parse a constant.
So can we just can you just put a comment about what AST stands for? What was it again? It was a
abstract syntax tree.
Abstract.
That's also a term you see very often with parsers. That is a tree representing your syntax.
Yeah.
And then there are other trees, but I never get to that point. Like if you look at in F# they have several trees.
Right.
If you look at compiler, because they're enriching it further and further and further. So let's try to define the const parser. How should we go on doing that now?
Question.
It's simpler than you think.
It's going to be an integer, isn't it?
Yeah. So if you type the integer parser right,
oops,
in wrong place.
Yeah. So it's going to be pint.
Yeah. Then you need to map this result.
Okay. So with the map.
And now you can use the new operator we did.
Yeah. Just trying to remember what the map operator was, and which is
it's height
greater. Yeah. And that's going to be.
And what should you put here?
Integer, I guess.
You want to make this into a const, right?
Yeah.
So you actually type const.
Okay, that's a type. Okay.
It's the big C.
Big C. Okay, wonderful.
And now if you hover over pconst, I hope it says...
Yes, it's a parser AST there.
And that's exactly what we wanted.
Yeah.
So...
Oh, yes, const, because we've defined it there. Okay, yeah. Got it, okay. Light bulb came on just then, yes.
So let's define a variable parser then, right?
This is going to be I guess a pchar.
Well, yes.
P string, isn't it?
We have a string, right?
Yeah, we have a string. Yeah, we do have a string. And this is going to be a variable.
And
I need let, yeah.
Okay. What is the type of P string? We need to check that. I forgot that. I don't remember that anymore.
It says it's a parser of string. That should be okay. Where's P string? Are we not defined P? There's P string is up here somewhere. Maybe it's a list. Where's P string?
I think I saw it. Should I control?
Yep.
So I take control then.
Yeah.
We are like pilots now.
Yeah.
That's saying in the cockpit.
There it is, yeah.
So that looks right.
It looks okay. It's a parser string, yeah.
Yeah. And so what is it complaining about? Expecting given a function type. Have we overridden this somewhere? let's try. Yeah, also a little bit surprising, right?
Yeah.
Let's do the pchar you suggested. And fun c string c. So what I did now, less elegant.
Yeah.
But I can't really figure out what was wrong right now. So we read a single character. We have a single character. We make a single character into a string. And then
cast
we
it as variable, yeah.
In a variable.
Yeah. So this is a lambda, basically. If there's C# developers out there, it's a lambda.
Yes. So the P string parser should work, but for some reason it didn't.
I think Parsers is saying that P string is not a parser, but a function that takes a parser.
Oh yeah, he's right. Yeah. Now he's completely right.
Yeah.
Let's keep this and implement it as it is, because we had the idea. We made a general one. So here we say pchar.
Yeah.
So what we wanted to say here was actually this is the
P
reason
letter,
we did
isn't
it.
it? Yeah.
This is exactly the reason we did it. Thank you for Boris.
Thank you much. Yes, keep us on the straight and narrow for Boris.
Yeah. But now I think we should try this. We should see if this thing works.
Yeah.
So if you go down to where let's use this parser. So let's say the let p parser here is equal to the const parser, and then we run the const parser on an integer and see what happens.
Okay. So let p equal p const, yeah.
Yeah. There's extra s here.
Oh, yep. So yep. And let's p run that. So what did you want to run it as a digit?
And then we send in a single digit, or send in 1 plus 2, but a string. And pipe it to printf, like we do on the line below. And we can comment out the other lines, right? So what happens when we run the program now?
Let's find out. We think it should come back with a 1.
I think it should come back with a const 1.
Yeah.
Did we save? No, we didn't save.
Oh, right. Okay. Let's try that again. There we are, const 1, and then position. That's right. Okay. So yes, it's the type T is const. Type const 1, yeah, and then 1 is the position, the next position of the string. So it's now our little position pointer is pointing at the plus sign now. Yeah, got it.
Exactly.
Yes, Boris, well done. Thank you.
Let's try the variable parser then, right?
Okay.
So if you say x plus 2, right, or something like that, and we run this through the variable parser. And you can replace p const here with p.
True. That's what we did, that wasn't it?
Yeah.
Okay.
Try this. Saved.
Oops. Don't seem to be able to type in the into the there we are. So you can come back with a variable x, which we do. The variable x in as a string, which is what we wanted.
And now we want to make something called a p term. And the p term in this case is either a variable or a const. So how should we write that? Right.
So that p term is going to be it's going to be p const.
Yes.
And then there's this operator, which I think is very descriptive, either that or the other one. P variable.
Yeah,
it's remarkable how, once you start to understand what these operators are doing, the choices make a lot more sense than they do when you first see these things. Yeah. So let's try P term then.
See how this thing, save it and run it. Oh yeah, we should also use it, right? Yes, exactly right. So then this should succeed.
So I think you've got the shared terminal, so if you want to just click in the terminal for me.
Ah, yeah, I do. That's cool. I got the link here as well.
Yeah.
Delete it. So I'm going to type .NET run, if that's okay by you.
Yeah, if you would do. I think we've lost our shared terminal.
Did you see the result?
No. I'm just going to close the shared terminal and restart it.
Intermission time.
Yeah. Let me go back. So this is just some of the interesting things you get when you work with live share.
Yeah, but it works kind of well.
Yep. So there, variable x. It's picked out the variable, and I guess if we change it.
Now, if you replace x with 1, it should just work.
Yeah. Come on, come down here. Oops. .NET.
.NET.
There we go. There we go. Const. So it's picked out a constant or a variable.
Yeah, that's pretty cool.
Yeah.
So what's the next step for us here? So okay, so we want to start parsing. We got pretty far, right?
Yeah.
But now we need a new kind of way to, or we could maybe do this with many, but I want to introduce a powerful, which I like, parser combinator, which is called pchain. And the purpose of pchain is to chain expressions together that are separated by an operator, and also giving it an operation to sort of join these things together.
Okay.
So that was a mouthful, but the idea is that we want to define a parser for the separator, which is plus, minus, and whatever, and we want to define a parser for the terms, and the terms should be separated by the separators, and we want to repeat it as many times as possible. Does that make more sense?
To work your way through the expression, yeah.
Yeah, and this parser here is. I think I'm going to help you a little bit here.
If you might, you'll have to.
Yeah, and then we're going to talk a little bit about how it works.
Okay.
Because it's a little bit. This is it's a little bit more complex, and it's not magic, but it's difficult the first time you write it. I'm going to find the p-many parser here.
Here it
is. So the signature to begin with will confuse. So I'm going to call this p chain L1, which is a name which you might think is weird. But the reason for this is we're going to chain, and we're going to keep this operator left associative.
Okay.
I'm not sure if everybody knows what left associative means, but it means like if it has something like this, 1 plus 2 plus 3, the parentheses are placed in this order. So the plus operator is typically left associative. If we have something which is right associative, which in F# is this operator. No, I wrote I completely messed it up. Sorry. This was right. 1 plus 2 plus 3.
Yeah.
This is left associative. That makes more sense.
Yeah.
Plus 4. But if you type an expression like this in F#, this is a right associative. So the parentheses are placed in this order instead.
Okay.
So in here, the parentheses come from the left of how we want to read it, and here it comes from the right.
Okay.
and we want to have left associative. The number 1 here means that we want to at least succeed with one term. You could, like with the many parser, you could imagine that we could allow a chaining operator that allows us to fail with the terms, but we want to always succeed with the term.
So we did do a many one, didn't we, which was the one or more characters?
Yes. So we're going to define a chain L1. Does this name now make more sense? I hope.
Hope so. Anyone got any questions in chat about that? If you have, just shout up. Looks like everyone's happy.
And then I'm going to define here, I'm going to type out the signature, but then I'm going to do it a little bit easier. So we have a parser T here, which is the term parser. We can call it term parser. And then we have a parser sep parser. And now, what should the type of that thing be? And I'm going to propose that a cool type of this parser is this thing here. Sorry.
Okay.
This was not obvious to me the first time. But this is, in some sense, a reducer function of a reducer function. So what this means, but why we use a set parser like this is we have two terms and we want to combine them into a new value t. So we succeeded parsing one.
Okay, right, yeah. I see. I get it, yeah.
Yeah. So how should we combine them? So the sep is then the combinator function. So to combine this.
Yeah.
This is sometimes called a semi-group as well, but never mind that. So that is the reason for this thing here. And then we're going to do it like this. Now we're going to loop over this thing because we need to do a loop.
Right.
So I'm going to write a loop, and this is tail recursion. We love tail recursion in F#. So we're going to have an aggregated value. This is kind of the result we're going to end up with, and we're going to aggregate that. So I call this ag, or what do you want to call it? Sum, or it's not really sum, but it's an aggregation.
AGGR then. Aggregate. That's it. Yeah.
Yeah. And then we're going to have a position, much like we have the many parser where we are moving the position. Yeah, we can call it the current pass.
Yeah.
Like up here, we call it values and current pass, not current pass. So it has similarities with what we're using in the many parser.
Yeah.
But now it's going to get a tiny bit more complex, and that means now I'm going to extract the term parser by using this syntax here, and I'm going to extract the set parser by using this syntax here. So this is a thing. This is also a little bit controversial in F#.
Okay.
Is that F# allows you to sort of reuse binding names. In C#, when you have a variable name, you cannot create a new variable name with a different type in that scope. Does that make sense?
Yes, it does, yes. F# you can do that.
Yeah, so we could give it a new name like this. Do you prefer that?
I think so. Or maybe funk. Does that make any sense? Or yeah. Yeah.
Is that
yeah.
Should we do that? I think that probably is good. For an F# programmer.
You wouldn't bother doing that, yeah.
Yeah, this is okay. But since we are in a stream where this is a little weird, we avoid that. So first thing we're going to run is so when we come into this function, we already have, in this function, we're first going to execute a separated parser to see if that thing works. So this is what we're going to do. We're going to execute a separate parser using the current pass.
Yeah.
With, And then we have it might fail, right?
Yes.
And if the separator parser fails, what should we do then? Well, that means that we were looking for a plus sign, but we didn't find a plus sign. But that could just mean that we have kind of reached end.
Yes.
And we're okay with that. It's nothing wrong with that. It's just that we have reached the end of what we can parse. So we should just return the result then. And we return the aggregate value and the current cost.
Okay.
Like up here, when we reached none, we were
We
done.
returned the list and reversed it. Yes, absolutely.
Yeah. Now, if we, now it's a SEP reducer. I can call it reducer SEP pass. So if we succeed, we get this reducer function, or the combinator function. I call it reducer, but maybe we should call it something else. SEP. What do you want to call a function like this? That combines two values. Should you call it combine?
Combiner, yes. Yeah. But you've got to be a bit careful with it, but let's try that combiner, yeah.
Yeah. In kind of function slang, it's like this is reducing.
Yeah.
It could be, yeah. Yeah. And what do we do then? Well, the next step we want to do is now we want to run the term function to extract the term value that we want to combine, use this separator function. So I'm going to execute the term function using the string and the set pos. So this is the case where we succeeded parsing this value here.
Yeah.
And now we're looking for the next term.
The next term, yeah.
Yeah. Match with. And now what happens if we reach none? Now here none is bad, because if we have a plus sign, we are really looking for a term here. It doesn't make a lot of sense if it looks like that. So in this case, this is no good. So if this happens, we're going to return none.
Yeah.
Indicating it. Otherwise, we're having a term value and term pos. And what we do then, well, we abstracted the term value, this thing here, and this thing here, and now we want to aggregate these two together or combine them, and we're going to look for the next term and separator.
Yes.
And this is meaning we're just going to loop here, and now the aggregated value will be set combiner, send in the aggregated value that we already have with the term value. So we aggregating these together, or we're combining them using this operator. And then we use the term pos. So now we are going to continue searching. Does that make sense?
Yeah. So do we need to change this name here, SEPfun, to SEP combiner then?
No, this is a separator.
That's
parser.
a parser. Okay. Fine. Okay, I'll get it. Yeah.
Let's leave it for now.
Yeah.
We're almost done. And finally, what we need to do is we need to parse the first term here. So here in this function here, we're parsing +2, +3, +4, but we need to parse
the first value. Yeah.
Yeah, and that we're going to do on the outside here.
Yeah.
And then we run
the loop. Yeah.
Term function using the pos here with at least I thought so. What did I type wrong?
It's the capital F. That's all.
Yeah,
Yeah.
and I missed here. So fun. We type none. And if this failed, there's nothing really to do. We didn't succeed, and then we have some term value, term pass. What do we do then?
We want to put that into the loop, don't we?
Yes. So then we give the term value and the term pass. So this was, you know, I hope it makes sense when I describe it.
Makes sense when you write it.
Yeah.
Yeah. Whether I could have come up with that myself, I don't know. I guess you start thinking logically through it.
You would, but the first time you write these things, it takes time.
Yeah.
And also these types are kind of, this is what I like a little bit functional block programming. The types maybe not are obvious, but they are kind of, they are flexible. So it sort of makes sense. But now we can use this thing here, right? We are now, if we've done this correctly, we can actually start writing quite complex expressions. So I'm going to let you write some code now.
Okay.
So I scroll down to the bottom, and what we need now is, to start with, we want to define a function that can parse a plus sign and return a function, this kind of the right signature that combines two ASTs using the plus operator.
Okay.
So how should we go about doing that?
Well, looking at your expression tree we're after, we're looking at something a lot of this kind of format, aren't we?
Yeah. So if you start with the plus operator, what we do is then we want to read a plus sign, and we don't care about the result of the plus of that operator. We just want to check that it is a plus sign, right?
Okay.
But then what we're going to return after that is this function. So did we define a skip character function? Do you remember that?
We did, yes, we did do.
So we can begin with that thing.
This is skip char here. We can start something like that, can we?
Yep. Now we're going to use
use it inside there, are we?
Okay. So P plus is using this thing here.
Okay.
At least that was I thought.
Okay, that's fine. So we're gonna pass in a parser. So that's going to be equal to
P skip char, right?
Yeah, P skip char, and then the plus sign, isn't it?
Yeah, I think it's character.
Oops. Okay.
And now this is not the right type. We want to return a binary operation. So one way to do is using this mapping operation, and you write the function fun character. You have to write it before fun c. That's mean fun c. Okay. Arrow. Char is a function that's confusing to me.
Okay. So
yes, fun c is. But we don't care about it because we know that this character is plus because of how skip char works.
Yeah. Okay.
So what we want to return now is a function that accepts two values, left and right, and returns a binary operation. Returns a binary operation that combines these two ASTs into the binary into a plus operation.
Okay.
So you're actually returning a function here instead. So that's extra confusing. So, but a function that takes a left tree and a right tree, and this function returns then a binary operation. Maybe make a new line here. Yeah. Make it. Make a new line. I think this will confuse the compiler. make the if can I write?
Yeah. Okay.
This is less confusing to compile often.
Okay.
And the binary operation, right? And the left tree is then, the first argument of binary operation is then the left tree, because if you look at the definition of a binary operation, you have, but you have to type parentheses in this case to construct it.
Yeah.
And then you type comma, and then it's the binary operation, which is then the add operation, right?
Oh, I get it. Okay. Binary opposite.
You don't because we don't require. You can just type add.
We just put plus sign in there, can we?
No, add.
Add. That's it. That's the type here, right? Okay. And then write.
And write. And what is the type of P plus now?
Yes, that's the right type, isn't it? So it's the T to T to T.
I'm waiting to see it on the stream here now.
Yeah.
It's a few seconds delay. I mean, see if you hover over there. Yeah, that looks good, right?
Good, yeah.
Let's try this parser to see if it succeeds first before we start chaining it. So if you scroll down to you exchange this with the P plus, and then we remove the first one in so it's just a plus. And you see what happens if we run it. It probably, yeah, right. So it doesn't make a lot of sense because it's some function.
Invoking a function of some kind, we can't see what the function is, yeah.
Now, what we can do is using the chain function to chain our term parser and our plus parser together. And hopefully we can start writing more hopefully we can start writing more complex expressions. So shall we try that?
Yeah. We're going to do a P chain.
I would actually write this as its own expression.
Okay.
So you could call it P like under P term. We make a new parser, which let's call it PAST because we're kind of getting there. It's not complex. It's not complete, but it's a start. And it's equal to the P chain L1, P term, and P plus. And you misspelled term.
Yeah, well, that's just me all over, isn't it? Misspelling everything.
So let's see if this. So what we want to see if this succeeds is a single 1 should succeed, right?
Yeah.
A 1 plus 2 should succeed.
Yep. Let's go through all those.
Plus 3 should. So let's try all these cases. So if we copy paste that line 3 times, the P run there, we can try 3 different cases in one.
Good point.
It's good.
So P plus 1 plus and 1 plus 2, yeah.
Yeah. You want 1 plus 2. The first case to be no. Yeah, exactly right. It worked like we expected, but yeah. I was hoping we should write complete expressions. So 1 plus 2 is the second case, and the third case is 1 plus 2 plus 3.
Okay. So it worked okay. We got the none back from when we couldn't pass, so that's at least proven that case.
Try this on.
Yeah. Wow, it's building that expression tree really nicely now, isn't it? Look at that.
Yeah, and it's left associative as well because we see const 1 add 2 const 2 3, right?
Yeah.
So now we're getting there, right? Now we're getting to something here, really, and we're not so far away to actually being able to parse. Fubaris asked it why was it null instead of none, and that is a bug. I think you can argue that it prints none as nulls.
Yeah, I found that early on when I was starting to play with F#. I was very confused And I was trying to output none, and it came up with null, and I thought I had an error, but it's actually just the way the F
And I suspect the reason for that is that the representation for none in F# internally, I think, is null.
Mm.
So this some option value is actually has special cases, because for all other union cases, if you would define it yourself, none would actually be an object, not null. Okay.
And that's one case where you could actually define it, couldn't you, yourself, so that it came out nicely.
Yeah, but I think they do this for performance reasons.
Yeah.
And I also think that the F# compiler understands option. You know, it has an understanding what that concept represents.
Yeah.
The reason we use %A is that it gives us a nice. For Parsers asking a question in the chat, it prints we get a nice printout of the expression tree.
We haven't got to think too hard, have we? It just prints out whatever is in there. So
yeah. Shall we define the other 3 operators then?
Yeah.
So, because if you define a p plus, a p minus, and a p multiply and a p divide, we can just make the operator by ORing it together, like we're doing with p term.
So we just create a p minus, yeah.
Now, I'm going to ask you, do you want to, because what you're going to notice now, like you're doing that thing here, right? And then you change the minus and subtract, right?
Yeah.
You just change in 2 places.
Yeah.
So we should introduce a p operator pop thing, right?
Yeah.
And that's quite simple to do, because the only thing you do here is, like, if you copy paste p plus again, and then we call it, I don't know, p op or whatever. Yeah, have a good sleep for Parsers.
Take care. Thanks for joining the stream. It's brilliant to see you, and thank you for the follow.
An example, you call the first one operator char, operator char, something like that, or op char. I don't know what you want to call it. The first argument.
P op char, yeah. The argument. Okay, right, yeah.
Yeah.
So we wanted skip char. We wanted a variable character.
Yeah. So yeah, exactly. You just add it up there, right?
Yeah.
And then you added another argument for op, maybe just op. I don't know what to call it. Operation. Yeah. Operator. Yeah, that's good. And then you use the operator down there. And using this, we can now define p plus and p minus using pop.
We better move this up to the top first.
Yeah. And we copy paste this 3 times.
Yeah.
So, and then we make plus minus and plus subtract and multiply and divide. So this is a little bit like the satisfy parser we made before, right?
Yes,
so
it is, yes.
And you need new names for these functions. and then we create. You can remove the p minus there below. And I don't know what to call this. Maybe we call this p all op for all operations. And you parser, right? Yeah.
ID trying to help me.
Yeah, I know what you mean. All up. And that is equal to p plus or p subtract or p multiply or p divide.
So these operators start to become really powerful here, don't they? Very expressive. Where's me? P subtract.
P subtract, yeah. So, and maybe we should call it P, instead of P plus, we call it P add to keep it consistent.
You're right,
yeah, that was my mistake. I called it P plus, yeah. And now we should be able to say that the AST now is P AST, P term, P all up. Right?
Okay, I misspelled it. Just the spelling. There we go.
And if you go down now, you can just run it now to see it still works, right? We haven't broken things. Duplicate value.
P add. I've just got P add somewhere. There we are.
Oh yeah, that one. Yeah, now we have a much better P add now.
Yeah. Just get good at that. We got two P adds, have we, somewhere?
Yeah, I found it.
Oh, there it is. Yeah, we can get rid of that, can't we? I'll just comment it out.
We can comment things out here, right?
Yeah.
Yeah, that might work. Okay, let's try this. See if the thing works.
Come on, where are you? I think it's going to work. There we go. So it still does the 1 plus 2 plus 3.
So let's try to put in a minus sign and some maybe multiplication.
So it's not going to get the association. The association is going to be wrong, isn't it? Because of the precedence of multiply. But we should get.
It's going to play last now.
Yeah.
So, but we're going to fix that.
There you go. So it's parsing it correctly. It's just the precedence which is wrong. So I think we're winning, aren't we? Here, definitely winning.
Really getting there, right? This is pretty cool stuff, I think. So now we are parsing a quite complex expression. So how do we go about implementing these precedence things?
Good question.
Yeah, good question. It's not obvious the first time you do it, but then it gets easier. So the way we will do it is that we will introduce two levels. First, we're going to try to parse with the separator multiply and division because they bind harder. So we're going to start with that. So instead of having all up, we will have like, I don't know what to call it. I sometimes just call it op 0, like level 0, and then op 1 for level 1. Or then sometimes I call it add like and mul like, multiplication like, because we have a precedence like addition and we have precedence like multiply.
I'm going to call it that.
Yeah. Do that. And now this is just equals to p multiply or divide. So what will happen then is we're going to parse using that separator, and then it will parse as many of these operations as it can, and then it will fail, and then it will fail on the addition and minus, but then they will take on in the secondary level. So it's a little bit weird, but it's going to work out.
The great thing about this is how you kind of build it up in layers, don't you? So you're just laying more complexity on top of each other, and you can actually prove each micro function we build up, each parser we can test individually, and almost by definition, if you combine two parsers that pass their test, then there's you can't get the higher level one wrong in many ways. I mean, I can see you can by just making wrong assumptions, but we're building things up from we're building molecules out of atoms. So the atoms are correct, but the molecules can be right. Yeah.
Yes. And as we said last time, let's not be too cocky. But so far we haven't debugged this.
No, that's right. We're not all we've done is run a sanity test and run it and see if it comes back something we suggest is correct, and it has every time.
Yeah. So let's create. So now we're combining. So now between AST and P term, we're gonna write. I don't know what you could call it. You can come up with a name, but we're gonna run. What we want to run is chain with the multiply or divide.
Okay.
So maybe that is the name. P chain multiplied or divide. I don't know. Yeah. Equals to P chain L1 P term, and then this P multi or divide. That one, yes. And then we take the next level, and that you can call P chain add or subtract, or how you want to call it. Same as above, except but now you use the P chain. No, not the P term. Now you use the P chain multi or divide.
Oh, okay, right.
So, like you say, no, not the one. The P chain. This thing here.
Okay. This one here.
No. No, we want to chain these things together now. So instead of P term, we're chaining these expressions.
So which expressions are you pointing at? I can't see. P chain.
I'm going to type.
Okay then. Okay, got you.
So instead of chaining terms together, we are chaining
expression trees together. Yeah. Well, segments.
Terms that are defined using multiply or divide.
Yeah.
Let's see if that thing works out as we wanted. So if we save this thing and we run it, what happens? I can't save it, so you have to save it.
Okay. So we're currently we'll add and subtract, change subtract. So that's that one there, isn't it? Okay, let's try it.
Hopefully it works, right?
Okay, there we go. So
the first two were the same, but the second one changed the shape.
It did.
And if you read that thing, what happened was that in the inner level here, const 3 multiply const 4, that is in the inner level now. So that is evaluated before the subtraction. Was it correct? Yes.
Yes. So it's doing it correctly, yes. So it's going to multiply 3 and 4 together first, then it's going to do the one plus 2 minus whatever the result of that is.
Yes.
Yeah.
So then we got the precedence here, right?
Yeah.
This is now we're getting somewhere. Now, so this is the thing. This can be actually quite hard to do with regular expressions, and very hard to do with regular expressions in a single regular expression.
Yes.
So now we're getting. So if you start asking me what is the point of parser combinators, well, they're type safe and blah 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 blah, but they can also support things that regular expressions
can't do. Yeah.
And of course, you can type x and y's instead of 1 and plus 1. That should work, right? So should we try to introduce some x and y's and things like that?
Let's do that.
Because that should work too.
So x plus 2 times 3 plus y.
Yeah, sounds good.
And there it is. Variable x, add 2, and
Yep.
subtract that from 3 multiplied by y. Or subtract 3 multiplied by y from x plus 2. Excellent.
Yeah, really good, I think.
Yeah, absolutely. We seem to have come such a long way from where we started today, because we started off still, very much working with simple parsers, and now we've got an expression tree like that, which we can then presumably parse through and actually evaluate that.
Yes, we could implement it depends on what you do. We can implement an eval function and toString function, or we can continue making our parser more what shall we say, complete.
Yeah, let's do that. Let's try and get a complete parser. Yeah.
Yeah. So I think the next step we want to do is implementing parentheses.
Yeah.
And so let's think about how to do that a little bit. So if you scroll up to the p const and the p variable on top here, maybe I control for y.
Yep.
So
it's jumping around a bit there. I'm not touching anything.
So a parenthesis, right? This will introduce a kind of a little bit of challenge to us now, but it's resolvable. But I'm going to introduce a new helper parser to help us doing this. So how do we do this thing here? Well, with parentheses, we start with something, and we have a sub expression here, and we have an end parenthesis.
Yeah.
And this can be implemented as a term, and I will type it out a little bit, and then we will point out what the problem is.
Okay.
Yeah. So this is kind of a sub expression like that. And now we're going to use skipchar parentheses, and now I'm gonna use the operators.
Take the right hand side of that, yeah.
St and p skipchar.
Oh wow, that's really impressive.
And yeah, messed up there, right? So the way to read this is we parse the parentheses, we throw that thing away, but it needs to be there, and then we want to read the AST, and then we keep that result and we parse the end parentheses.
Throw it away, yeah.
And this now, the reason I type AST here is because this is the full sub expression kind of here that we want to do.
Yeah.
We want to sort of go recursive, and that is the problem here, because F#, the way F# works, it doesn't allow us to it doesn't allow us to do this, because in F# things has to be declared in order.
Yes.
So in order to support this thing here, we will introduce a forwarding parser that allows us to sort of declare a stub for the AST. And then when we have the AST, we're going to say, okay, this is like forward declaration functions kind of in C++ if we have done that. It's a little bit ugly, but it's going to work.
Okay.
And I think I'm going to implement that thing for you, because this is a simple one, but this is also one of the things that is hard to come up with. if that's okay by you.
Absolutely, yeah. Carry on.
So I'm gonna go up somewhere nice. Maybe we would do it here. So I'm going to pick a name which might seem odd to you, but this is this is to keep it compatible in concept with fparsec,
Okay.
because I have the dream of making our code mostly compatible with fparsec.
Sounds good.
So we create a class which is called pCreateParser forwarded to ref, which is a weird name. But the thing, this will return a parser t, which is kind of our, and this parser t is kind of our parser that we can use, that is forward declarated, that is not fully defined yet, but we can use it in place where we need it.
Okay.
And the second thing we return is a ref variable. Do you know what refs are in F#?
No.
It kind of is a mutable variable.
Okay.
So this ref thing here allows us, when we finally have the value here, we're going to mutate this ref.
Okay.
To point to the real parser. And now this parser here will use this thing here. So you could imagine this is a variable. This, yeah, you're going to see what happens here.
Yeah.
When we just... So we start as we always kind of start, right? We're doing these low-level parsers. So where did it go? I don't know why it's jumping around.
No, it's jumping around a bit. I'm not doing anything at this end. I'm just following you. So there we are.
Yeah. Okay. When I scroll using keyboard, it works better. I scroll using the
mouse. Yeah.
So I'm going to define, the first thing I'm going to find here is a kind of a dummy parser. No, that's actually, I'm going to do it. No, so this is our forwarded parser, or parser, we can call it like that. Oh no, this is no. Sorry. So I'm thinking on on top of my head. So this is the parser that always fails. The reason it fails is this is the parser that is called when
we haven't got a parser.
Yeah. So forwarded parser not initialized. So if this exception happens, we have not coded correctly.
Yeah.
But this is just a dummy one. This is just, we need it. And then we're gonna create this ref parser, ref2 parser, like this ref, and then this we initialize to the dummy parser.
Yeah.
So it has a valid value, but it's a dummy parser. And then we're gonna declare our forwarded parser, forwarding parser perhaps even.
Okay.
And this thing is going to do is something quite simple.
Okay, so the color change is interesting that's going on there.
Yeah. So the thing is, we have a reference to parser here, and this is how you deref it in F#. Okay. We could make it mutable as well, but I'm not going to do it. And now, oh boy, what did it go? It jumped around again.
There it is.
Okay, and now we're going to run this parser using this thing here, right? So we read the ref parser, we extract the parser function, and we execute it. And if we haven't changed this parser, we're going to execute this dummy parser and fail.
Yeah.
And finally, what we're going to return is the forwarding parser. Forwarding parser, right? And the ref2 parser. and hopefully that our types match up now.
Looks good.
Okay, it looks like they did.
Yeah.
So
the color change of the variable, is that to show that's a mutable
yes.
variable? Yeah, okay.
Yes. This is sort of an idea to show you that we're dealing with mutable state.
That's good.
That's good, right? So now we can use this thing here to create a forwarded AST parser, which we can use in our what's called in our parenthesis parser.
Yeah.
So let's see if we are able to do that. Boy, I have to scroll with keys.
Yeah, there's still a few wrinkles in live share, I think.
Yeah. So I'm going to call this forwarded AST p ref to forwarded AST, something like that. And what did I fail with here? Do I need to type in? I thought it could infer that, but maybe it can't. Maybe it can't. Okay, I can.
It wants,
okay.
Yeah, wants explicit type arguments, doesn't it?
Well, I'm going to do it this way for now. I'm going to fix this thing here.
Yeah, type T, okay.
So we require. It works.
Yeah, that's
so
good. I understand that.
Yeah. So now, if we run this thing and then, in addition, now we say that the sub expression or our term parser now. Wait, where's the term?
It's a bit like there it is, yeah.
Yeah. It's now a sub expression as well.
Yeah. Or a constant or a variable, yeah.
Yeah. So the only thing we kind of have to do here now, when we're done, is that I'm actually going to do it this way. I'm going to initialize this value now. Can I do it this way? P for, ref. So this is the complete expression parser. So when we have the complete expression parser, I initialize this. I say that this pref to parser, this is how we write to a mutable.
Right, okay.
Yeah. I usually write this as do, this thing here. I just like that kind of better, but I don't think it has any difference. So we execute this thing here.
Yeah.
But so this is what we do. So now when we do this correctly now, this means that now when the sub-express parser tries to run, it should actually run this thing here.
Yeah. So you basically, it's like a delegate almost, isn't it? This is like a pointer to a function. You're passing that reference to a function into.
Yes.
Yeah. Okay, get that.
So we create a forwarded parser because we need kind of to create a recursive parser here.
Yeah.
And because F# doesn't allow us to do that, because F# requires functions to declare in a certain order, we create this forwarding parser that the initial, so we have a name, but that parser, it just crashes. But when we write this thing here, now it instead will execute this parser here, the paint, chain, and add, and that's what we want.
Yeah.
So shall we try this as a test case now to see if this thing works? You know, it's a little bit scary to do this late at night. I might.
Well, I've every confidence. So this is going to be.
I'm gonna follow you now.
Okay. So rather than doing this.
You can type around the Y. You can type.
Yeah. Okay. So if I just put that, in fact.
Yeah. What does that? That should work, right?
Yeah. So that should be -1, shouldn't it? There. So it should be 2.
If you optimize it, but it will not be that.
No, but that's what we should see. We should see it wanted to do this bit as the innermost function, and then the multiply, and then the add.
Yeah.
We have the challenge is interpreting the output then. So let's have a look. So the innermost thing is 2 minus 3, which is exactly what we wanted.
Yes.
Then we're going to multiply by y.
Yes.
And then finally add x, and that's exactly correct.
Yes.
Well done. I'm impressed.
So now we have parentheses.
Yeah.
Try doing matching parentheses in regular expression. Try to make a secondary level of parentheses inside this thing here. So if you type parentheses like round 3 perhaps, yeah, you can do that as well. Yeah, sure.
So now we've changed the precedence. It's going to do the add before the multiply.
Yes, if this works correctly.
Yeah. So let's look. So I think that's correct, isn't it? Because we're going to do this part first, then we're going to do this part. We're going to add the x, and the last thing we do is multiply the whole expression by y, and that's what we said there. Excellent. Yeah. That's fantastic.
So this is. I would argue that this is. This is quite powerful.
Yeah, absolutely, yeah.
And we have kind of a functional way to sort of parse expressions, mathematical expressions, which are not very complicated, but we have precedence support and we have parentheses support.
And it's in the natural way you write mathematics. So when I did a calculator, I used reverse Polish notation, which is a hell of a lot easier to parse than this. So we're actually using natural mathematical notation. So that's kind of, as someone who's had to resort to the reverse Polish, then it's very impressive.
Yeah, and so this is pretty cool, I think. So with this thing here, we actually come as far as I hoped we'd get. And it's precisely 12 o'clock at my side.
Yes.
But I wanted to. So, do you have any questions before I'm going forward?
I don't think so, because the questions are going to come later. It's because you've built up a really nice story of how we're doing these combinators, and it kind of all hangs together in my head because we've done it step by step. It's when all the questions come later when. The stream's finished, and 2 days later I look at the code and I think, what the?
Yeah.
So that's when the questions come, really.
But I think maybe the idea is that like we have parsers. We start with something very simple, and then we start combining these parsers to make them more and more complex. But all of these are always parsers, so we can always combine parsers again and again into bigger and bigger parsers. And as we kind of, maybe I think you commented that we're building things up from smaller and smaller things and bigger things, and it makes sense. It's kind of, we can predict what will happen, and it actually it happens like we wanted it to do. When we're building these parsers up in this way. And this is. There was a presentation last week. I wasn't there, but the guy linked it, and the title was something along this line: when everything fits together, like composability. And I think this is the case when you write parsers this way. It's like everything just fits together, and it just works. And it's so seldom for me that that is actually the case when I do programming, because often it's like, it fits together with a lot of duct tape.
Yeah.
but here it's like it fits together like a mathematical expression. Like we
That's exactly what it is. You're right. It's a mathematical expression.
We kind of build an algebra that allows us to sort of combinate parsers, like we combinate 1 + 2 - 3 × 4. This is predictable. We know what happens. But with our algebra, if you scroll up here to when we define our term, for instance, I'm going to scroll up here. So we define our term, or do you have that?
Yeah. There we are.
Now, so we're saying sub-expression or constant expression or variable expression. That is like we're writing an algebra here.
Yeah,
like,
they're basically, we're writing mathematical axioms, aren't we? We're saying these are the fundamental truths, and you start off with very simple truths and just build them up, and that's how you start off, as I think I said last time, you start off with, addition, multiplication, basic arithmetic, and number theory is very complicated, but behind there's these simple axioms that define what addition is and what multiplication is, and you can end up with as you say, we can have the integral calculus at the end of that, and then we can go on beyond that to the wild and wacky kind of frontiers of mathematics. What you've done here is just defined a set of axioms for combining parsers, and then you've built up that into almost to any kind of complexity we want. We could carry on and on forever with this and make more and more complicated things.
Yes, and whenever we combine something, it's always a parser, and that it's sometimes called that we are closed under parser type.
Yeah,
and that means we're always under this. That means we can continue to combine and combine and combine, and we can take a super complex parser and combine with another super complex parser, and they will combine.
They can't not combine, can they? Because they're all the same type, and we've defined what the operators on that type are.
Yeah, we can run the first parser first, and then we can run the second parser then, and we can combine these results. But because these complex parsers, even though they're very complex, they follow the rules of the parser, which means that we can continue binding. And that, I think, is very seldom for me, that when things get more than trivial, they never really combine well. It's like I have to put a lot of silver tape on the edges and like hope for the best. I want to find I don't think we have so much time to sort of define this thing, but I want to find an example now. So if you give me a few seconds,
sure.
I'll try to find. So there is something called. Do you see my cursor?
Yeah.
There's a library called fparsec, which is really cool, and I'll dump the link there for this thing here. And that is a parser combinator that is built in a similar style as we just built our parser. And I will try to see if we can find a good example that we can understand now.
Okay.
After defining our parser. So I'm looking here. Yeah, he's smart now there. Maybe this is a good part. So I'm trying to look and see if we can find a good one, and we can see if we can get that. Yeah, maybe this is a good. Maybe this is a little bit more complex one, but we can open this thing up and talk about it. I think if that makes sense to you.
Okay.
So I'm gonna share this under here. So the link I shared here is a JSON parser written in something called fparsec.
Let's go and have a look at that. Okay.
I'm just waiting for it to appear on your stream.
Yeah, it's the old stream delay, yeah.
So what you can see here, so this is using the library called the library called fparser, and that is a parser combinator framework that works much like we have it. But the two big benefits of using fparser rather than the thing we built here. One is performance, because our parser framework is not fast. There are reasons for that, and we could make it a lot faster by doing certain things, but it's not. But fparser is quite fast. In addition, and this is the big kicker, I think, is that if the fparser fails, it will give you a good error message saying, I tried this, this, and this, and this, and it failed.
Because ours just fails, doesn't it? It just returns null, and that's the end of it. Yeah.
Yeah, but fparser would actually say, let's say we typed in an operator that doesn't exist, like
exponential.
Then what fparser would say, it would point to the pipe and say, I was expecting a plus, a minus, a multiply, or a divide.
Right.
But we never put that in the code. It's just able to figure that thing out.
Right. Okay. That's really clever.
That's mind-blowing when I saw it. But let's discuss this parser here, what it does. So the way this is built up is like just with ours, that we're defining terms. So J null is the term in JSON, the null term. So string return means if it's a null, let's return J null.
Yeah.
So it's basically saying if the input is a null, return J null. If the input is true, return J boolean true and false. A number, now you can recognize a certain operator here.
Yeah.
A number is parsing a float and map it using the operator to J number.
Yeah.
So that was the reason I choose that maybe convoluted operator, is so that you can recognize this code and read it and see it. So does it make more sense now?
It does, yes. Perfect sense, yes.
Now, a string literal in JSON is a little bit complex, but this actually implements the full string literal using Unicode escaping. But we're going to scroll over this thing. Let's not look at that. Let's look at the J string here instead, where it says J string is a string literal that we pipe to J string. And then you see they also do this create for.
Oh yes, they do the same thing here. Yes.
Yeah, because they need, it's recursive, so they need to have a J value parser to do recursion. So they do this J value, okay. And what more do they do here? Yeah.
Exactly
so let's see.
Did, yeah.
So yeah, so he does a little bit scary, but J list is a list that is between the starting character, and he run a J value, and that is mapped to J list.
Yeah.
And what is the list between strings? Well, the list is between the open character, if you see that thing.
Yeah, we got it highlighted.
And the close character.
Yeah.
And then the WS is skipping white spaces.
Yeah.
And then you have a set by, which is kind of like our chain L, but not really, but is having elements that is separated by commas.
Yeah, so that's here, yeah.
So it's just a smart function to do all that thing. But it's basically saying between this open and end, repeat an element separated by commas.
Yeah, yeah.
And then what is a value? Well, a value is either, there's a choice right here. Instead of using this he uses choice function. So a value is either a J object, a J list, a J string, a J number, a J true, or J false, or J null.
Yeah, that's that bit there.
And then the final JSON parser is skipping the white space and the JSON value and skipping the white space, and in the end parsing the end of file character to make sure we don't have any trailing characters.
Yeah.
And that is our JSON parser.
So apart from a few kind of little wrinkles, we actually understand that just from what we've done.
Yeah.
Wow. Because I mean, if you showed me that code even
before,
you'd have no chance.
Yeah, but you also see here, like the JSON, we say white space, and we have this greater than dot. So we understand that we are reading the white space and throwing that away, and then we're reading J value.
Yeah. Yeah.
And a JSON parser is quite complex. Try to do that in regular expression.
Yeah, pretty impossible.
So that is quite difficult.
And that's 91 lines of code, and there's quite a lot of commentary at the start of it. So, yeah.
Yes, and I think this is actually a compliant parser.
Right. Okay.
So that was kind of my purpose as well this evening to sort of, we build a parser, but we build it in such a way that we can understand how fparsec works.
Yeah.
fparsec has really good documentation as well, I must say. So I think if I'm going to link to the tutorial here now. So I'm back in Visual Studio Code, and I'm linking to the tutorial. But I think now with this, what we've done here, it's possible for you and for any potential listeners here to read this tutorial and make sense of it. In that saying, I kind of get how this works now.
I think so. Let's have a look at it. Yeah, so it looks very comprehensive. So yeah, we can certainly. I think what I'm going to do, then I'm going to take that as a challenge and see what we can do in terms of understanding this documentation. Fantastic.
Parsing a single float.
Yeah, so it breaks it down, doesn't it? So into each individual kind of handling white space, parsing string data.
Yeah.
Sequentially applying parsers. Yeah, absolutely. Yeah, wonderful.
And introducing binary operators. I really hope that it's because this is such an excellent F# framework. If I was to list my favorite frameworks in F#, I would probably say fscheck and fparsec. I think they are so good, so extremely good. And this was actually, I think, one of the first really good F# frameworks.
And it's completely built on functional principles, as I guess the best frameworks are going to be, aren't they?
And if you would crack open a code and read this code, you would be horrified. Because the thing is, in order to get performance, a lot of these things that we implement using pbind and we do all these things, he actually he does a specialized implementation. Right. And he does a lot of tricks to give you performance. Yeah. But the API that you see,
it's consistent, isn't it? It's simple.
It's very clean and consistent.
Yeah. And it's the job of the framework or the library provider to hide that complexity, that performance complexity away from us. And I don't mind if I don't really want to crack open the code. Just want to use their library. If you want to learn how they did the performance things, that's where you need to dig deeper. But as ordinary users, we're not going to be interested in. All we want is reap the benefits of it. So yeah.
Before we sort of stop talking perhaps about the reference, by the way, if you click that one, that's really good. So in reference you find things like fparsec primitives. There you find many of these bind and p0 and all of the things we defined and the mapping operations. So that is kind of that thing. The char parsers are specialized parsers for parsing strings, basically, because you often do that. And so they are specialized. They have better performance than what we had in our case. But there's a little bit of gotcha with fparsec, but they do it for the good. And that is fparsec doesn't support lookback out of the box.
Right. And
the reason for that is fparsec wants to support parsing gigabytes of files.
Yeah.
And it's hard for the parser framework to know, well, how much of these gigabytes of lookback should I need to support? so it doesn't do that. So if you need if you need lookbacks, you need to put in an attempt that says, okay, I need to go back here.
If you failed,
if I have a failure.
Yeah.
So what could that be? Well, that could be, let's say you want to parse either an integer or a double, for example.
Mm-hmm.
So then you start by trying to parse, let's say, a double, an integer, and then you parse and parse and parse, and then you find this dot sign, that indicates that this is a double, not an integer.
Yeah.
But then you already consume, like, say, 10 characters.
Yeah.
Then you need to go back 10 characters.
Mm.
And fparsec doesn't support that unless you do attempt. So then you would say attempt int. Because if you just did the int parser, it would read the integers. Then it would fail to do the lookback. But when you say attempt int, then you support lookback. And the reason you put that into the code is just to show that, okay, I need lookback here.
So you're being explicit about where you're going to need that, yeah.
Yes, because it's a performance implication.
Yeah.
And that thing. So that is a little bit of gotcha with fparsec, but it's fixable.
Yeah,
if you do by using attempt, and you can find in the primitives you can find the attempt function, and it's take the parser A to parser A, but it implements lookbacks.
I think that's looking through this code is going to be for a time when it's not, as you say, approaching midnight, isn't it?
No. But I really hope that this code makes more sense to you now.
I think it definitely does. Certainly, you've cleared up a lot of kind of confusion for me, especially around the kind of really strange operators that get declared, and actually how they're really quite logical. I mean, I'm just looking here. You can see here the one that we didn't define, but it's the one where you take both. It's the pair one, isn't it? So did we define that? Yeah. I can't remember. But there's the operator which takes both, runs parser A, parser B, and then gets both values. So yeah. So we got a question in chat, Mårten. I'm not really sure how to answer this question. It's from M8 Zuli, who's asking whether he should do applied mathematics or computer science at university. Well, M8, I think you should do what you're interested in. Are you interested in computer science, or are you interested in applied mathematics? You shouldn't, when you go to university. I mean, I was a chemistry graduate. I think Mårten you were computer science or software engineer, Mårten. But you never really know what you're going to end up doing when you come out of university. So my advice to anyone who's going to university is do what interests you. Now, I'm slightly biased, and I think you should do some kind of science, technology, engineering, or mathematical degree, because I'm not sure that if you're interested in media studies is particularly useful to humanity. But if that's what interests you, you go and do it. So do come back, mate, if you've got any further kind of clarification on that. But if you want to get a job, there are jobs in applied mathematics and things like actuaries in insurance companies. If you want a job in computer science, then you might study computer science. You may not get a job in computer science. You might find your interest go elsewhere. So all I can say is my only advice to you is do what interests you. I don't know if you get anything to add to that, Mårten.
So I did computer science, as you said. My sister actually did applied mathematics, but she kind of realized that computer science was fun too. So she added a few courses on computer science, and now she's doing data analytics and building data pipelines.
Yeah, so absolutely. So the whole kind of data science thing's open to you with applied mathematics. So, and I think there may well be a shortage of data scientists. So, yeah, you can combine both. Maybe there's joint honours at the university you're thinking of going to, where you can do applied maths and computer science. Quite challenging, but I'm sure you'll be able to do that. Okay then, Mårten, I'm going to let you go. I know it's very late your end, and you've got work in the morning. So thanks ever so much for the streams you've done with me. It's been absolutely fascinating, and really enjoyed it. What I'm going to do is swap over to our coding screen, and we're going to do some good, excellent. So what I'm going to do, we're going to have some electric elf, some hype for Mårten. Thank you very much for the stream. It's been well, it's just mind blowing. It's going to take a while to go back and actually absorb everything. But as I stand now, I actually understood 90% of what we went through, which is I think is pretty good.
The FS check that uses this kind of functional composition to do certain tasks. I kind of hope that this helps you too. This is not just about parsers.
No,
it's about
absolutely.
How to build how a functional framework works. And I hope that this idea of understanding the fundamental concept will help you understanding other sort of functional frameworks like Chiron and FSCheck.
I'm sure it will. I think it's just been a way into the kind of whole subject matter of pure functional programming, and a very interesting and fascinating way in, which is relatively simple to understand. The idea of wanting to be able to work your way through a string and interpret what each of those characters are is something that everyone's had to do as a programmer. So yeah, it's a very accessible way of doing it. And I think the way we built it up over these kind of, I think it's probably 4 or 5 hours, has really kind of brought that home as how you. I think you said in the first stream that kind of normal object-oriented development, you start off with a big picture and you break it down into chunks that become manageable. But here we're doing the opposite, and it's quite refreshing and enlightening, really, to do that and to see the different approaches.
And I don't think it invalidates the object-oriented approach.
No, not at all.
It's a complement, and it's good in some cases, and in some cases it's good to having opaque boxes that we don't know the details on the inside. So both are valid in my head.
Absolutely, I think I don't agree with becoming singing in different camps. I think you've got to embrace all the tools available to you and apply them where they're most appropriate. And maybe functional programming is. Well, we use functional programming every day in C# anyway. It's just hidden in the concept of link, isn't it? So it's not an alien thing. Really.
But the thing of link also, I read this on Quora the other day that they talked about functional programming there, and someone said, I don't see the use of F# or functional programming because C# has link. And my kind of response to that is, well, there's much more to F function programming than link, and that is a little bit what I want to show here.
Yeah.
What we've done here, we could easily done in C#, and it would look okay. But it's more than just link to function programming.
We wouldn't have learned so much, I don't think, if we just churned it out in C# because it's about the whole thing's about the learning experience of challenging ourselves to understand a different paradigm of programming. I think it's really valuable for every developer to do that. And you may be hitting your head against a brick wall for a while trying to understand it. But I think Mårten and I were talking before the stream, and every now and again you get these little light bulb moments, which kind of they may not open up the whole world of functional programming to understand those little bits, and that little bit of understanding you can then make informed decisions in the future about what style of programming you want to do in a certain situation. We could say, well, actually, Mario Tristan, thank you for the follow. That's very kind of you. Really do appreciate that. You can make more informed decisions in the future and adopt the appropriate style. And more of this functional style is coming into C#, and the pattern matching is the thing, the kind of the latest kind of round of things that we've now got. Switch expressions with full pattern matching. And
I'm really hoping for algebraic data types.
Yeah, and
I think it's
could
such
come.
an important thing.
Yeah, and that could welcome. So, yeah.
So, but I also want to wrap up with how far can you take this pattern, this function composition pattern? And one of the coolest thing I've done, and this is not my idea because there's no new ideas, but I read about this idea and I re-implemented it. But I think it's one of the coolest thing I've done, and that is creating a functional framework for building forms.
Oh wow!
Instead of writing parsers, I build forms for input and output using this style of programming. And I think that's pretty cool that you can actually take it that far.
Yeah, because often you think the functional style is like this. It's quite mathematical, but there you've taken it into a completely different realm, haven't you? That's amazing.
Yeah, and kind of creating an algebra for forms, which is like you would think is completely sort of no, that can be done, or something like that. Give me a second. I will just see if I can find a link that makes sense to you, that you could see. We're not diving into this, but I'm just seeing if that is. Yeah. So just a few seconds here.
No problem.
Yeah. So I'm going to share a link with you here, and
I'll pop this into
we don't
chat
go into that, but I wrote a blog about this, why I think this is important.
I'll just pop it into chat.
So we can scroll down to how the form looks, and you can see the idea here is that I want to be able to define a form using composition and sort of build it up. So in the simplest case, it's just a single input line. But then using composition, I build up a more and more complex form. And you can see we use this computation expression builder here.
Yeah, formula thing, yeah.
And you get validation and all of that thing. This kind of built in, and these can, as parsers, they can also be combined. And I think that is fascinating. So that thing you see there on the screen, the new user, that's what you write to get the form below, which is the new user form. So if you scroll down a little bit there, so and you see you have validation and all these kind of things. That's how I want to develop forms, kind of, to sort of do it quickly. So I think so. This pattern of function programming can be applied in ways you might not think is possible.
Absolutely, you would never imagine it doing formulas like that, no.
Yeah, and you see this checkbox here. Do you have a nickname? What will happen if you run this is that when you click it, it disappears immediately. So it reacts on your input and output.
Right.
At once. But the code for that is this if statement up in the formlet. And that so we don't have any events or these kind of things. We are coding without events, but still we have reactive forms.
Yeah, absolutely. It's amazing, isn't it?
So that's just an example of sort of, taking this in a different direction. But it builds on the same thing, actually, as with the parsers, in that we are defining what is a form, the atom, like with the parser.
Yeah.
What is the form? And then we're building bind, the bind operation. We're building all these kind of operations we build for parsers. They obviously look different because it's a different thing, but we build all these operations. And then we can actually start working with the form and combining them exactly like we are combining parsers. And the forms becomes predictable. Like we have a big form here and we have another big form here, and we could put them together and they behave like they should behave.
Yeah. It's that kind of, so that's what we said before, isn't it? It's that idea that if the atoms work, then when you combine the atoms together, then the whole thing's going to work, and then you've got arbitrary complexity at the end of it, because you've designed an algebra of input forms.
So this was just an example I wanted to show, sort of push for that it's possible to sort of take it to a different level than you would think, perhaps.
Well, here comes SourceScoop with the raiding party, so we better.
Are we about done here?
We're about done, yeah. So we'll defend our stream with some alfs. This is the new alf emote that we've got here. Welcome, SourceScoop. Thank you for the raid. We are pretty much coming to an end. We've had our minds melted again by Mårten with Parser Combinators Part 2. We're just now looking at wrapping up and looking at some code that Mårten's written to actually apply functional programming to input forms. So amazing stuff. So once again, Mårten, I'd like to extend my thanks to you for coming on and give you some cheers. Thank you very much, and we'll perhaps think about a future stream where we can take it even further. But I do appreciate you having to stay up really quite late your end. So thank you very much for the stream, and I'll let you go. So cheers again, and we'll speak again on Discord.
Thanks.
Bye. Okay, hello there, all you raiders. Good to see you. So hello, ASG, Fetchy's Face Eye, SourceScoop. Yeah, so we've been doing a lot of F# today. This is what we've been writing. If you're an F# programmer, then all this is going up onto GitHub now. If you're not an F# programmer, then what I've done with the first stream we did, which was 6 episodes ago, I've actually been through and made a lot of comments into the code, which are my interpretation of what we did at the time. We've added quite a lot to this today. So the aim of the first stream was to be able to simply parse 1 + 2 string and actually get an integer out of that. What we've done today is extend that almost exponentially to be able to parse any arithmetical expression, including ones with variables and with parentheses and with proper operator precedence. So if I come down here, we're successfully parsing, for example, this expression. We're not coming out with an answer, but we're coming out with what's called an expression tree. So this is the result of that parsing, and this includes the correct precedence implied by all the brackets. And if you don't have the brackets, you use default precedence of the operators. And we've built that really from scratch, just from kind of atomic building blocks. And it all started back here about 4 or 5 hours ago and several days ago on the other stream, with a basic definition of what a parser is in our world. There could be many definitions of this, and then a basic function which takes a string and extracts a character from a position in that string. And then we built all that complexity up as we go down here from just those two kind of atomic building blocks. So it's been quite fascinating. So I'm going to push this up to GitHub now, and I will go through the code. I usually try to wait about 5 days. ASG Gab, thank you very much for the follow. That's wonderful. Thank you so much. Let's switch over to our. Oh, we've still got Electric Alf on that one. Something's gone wrong with Alf. So thank you for the follow. There's some hype for you. I'll just go back to my coding stream, my pair programming. As I was saying, all this code will be up on GitHub momentarily. I will go through in about 5 to 6 days time and comment the code, the extra code we put in. So I'll just commit that. So what we've done, we've defined a whole bunch of new parsers and parser combinators, which are what join parsers together. And all of this is going to really take quite a bit of thought of how to describe what these things do. But we've even created our own set of operators here. And these operators look really scary, but actually, as we built them up through the course of the stream, they were really quite clear. So ASG, so you've not seen F# before, it's new to you. So it's scary to begin with, but it's really worth trying to get a little way under the skin, even if you don't think you're ever going to use it. A lot of these functional ideas have bled across now into modern C#. But what we've done here is really pure functional. So do take a look at the repo. I'll just sync that up to GitHub. Did it sync up? Oh, yeah, it's gone. You can get to my GitHub over here. So that's posted into chat is the GitHub repository. There's quite a few projects up there, including the bot, which is running at the moment in chat. The bot has a number of commands, which if you type !help, it tells you the commands that my bot applies. I've also got a couple of other bots running. We've got Nightbot who's doing moderation for us, and also CloudBot that's giving some extra commands like uptime. If you're interested in that bot, it's a multi-platform bot, so it's not in terms of it runs on different operating systems, but it actually runs in Twitch chat. It also runs on Discord and Slack. So that bot is currently running all 3 of those locations. So yep, check it out, SG. The video on demand will be available in this location for 60 days from now, and after about 24 hours it will also go up to YouTube. So all the other prior episodes of Codebase Alpha are up on YouTube, and there's the YouTube channel. If you would care to visit and subscribe, it's free and just help me out if people subscribe to YouTube for me. On that YouTube channel you will find such topics as building an Alexa skill from scratch, an introduction to using GraphQL as an alternative to REST API, and also our latest project, which we just finished, was building a artificial intelligence conversational chatbot using the Microsoft Bot framework. And our next project, which we're going to start on Wednesday, we're going to be looking at digital audio programming using a library called NAudio. And what the plan is to do is to build a simple synthesizer using NAudio. We're going to use our keyboard as a kind of piano keyboard, or a section of a piano keyboard, and we're going to play notes. To begin with, it'll be a monophonic synthesizer, but the intention is then to make it polyphonic, so we can have chords, and also to building things like envelopes for notes, and then build instruments, so we can have kind of a harmonica or an organ, or I don't think we'll be able to do a piano, but we do kind of different types of instruments, and then maybe have some visualizations like a spectrum analyzer in the GUI, and lots of kind of slider controls for volume and attack and release and things like that. So that's the next project we're going to be working on. We're going to start that on Wednesday. My Wednesday stream starts early in the UK, so it's going to be at 4 o'clock in the afternoon UK time, 1500 hours UTC. It will also be on video on demand, and then we'll continue that project over the next few streams and see how far we get with it. I do some pop-up streams occasionally, so sometimes I might have extra streams, and in which case your best way of keeping informed on that is to hit the follow button, and then you'll be notified when I go live. You can also go over to my Twitter and follow me on Twitter, so at CodebaseAlpha, and that does help me out as well, because it helps spread kind of the message about what Codebase Alpha is all about, which is introducing topics that you may not see on other streams. It's very much a coding focused stream rather than an entertainment stream or a chat stream. It's we do have special guests on it occasionally. So we had Mark Miller on a couple of weeks ago showing us Code Rush, and then we've had Mårten on twice now with this F# project to build the Parser combinators. So that's the plans for the next few streams. ASG, you love coding. You're in college right now. It would be year 4 in September. That's great. You want to be a software developer, yeah. So you don't have to. I mean, I don't know these days what it's like getting into being a developer. I'm a chemistry graduate. I didn't do computer science at university, so I kind of worked my way into this. Parsers, thank you very much for the follow. That's really wonderful. I really do appreciate every follow we get, and we are really heading towards our goal now. We're just 8 follows away from the 200 follower goal. So thank you so much for helping me towards that. It's I never kind of cease to be amazed by the community that we're building up. It does seem that live coding has really taken off in the past few months on Twitch, and it's really great that people are kind of embracing it. You know, on Twitch, Parsers. Yeah, so I'm a member of the Live Coders team on Twitch. So there's about 50 of us, all broadcasting really kind of diverse set of content, all built around development or even hardware. So there's people who do build keyboards, work with Raspberry Pis, IoT development, that kind of thing. There's pure programming streams like myself, mainly focused on .NET, F# being a .NET language, of course. And then there's people who do JavaScript, do Node, do React. There's another chap called Gareth Hubble who does C++, F#, Rust, that kind of thing. So there's a huge variety of things. So check out the Live Coders team for lots of other people to go and watch, and give them your support as well. That's fantastic if you do that. So you're registered mainly for JS and for C and for IoT. Yes, all very interesting kind of subjects, especially the Internet of Things is the up and coming thing. So Better Owen says you live in the live coding group. Been great range of things to have on in the background while working on projects and remote clients. Yeah. So I agree. It's an amazing resource that is developed now on Twitch. Something which we couldn't imagine even a couple of years ago. I think there were a couple of programming developers, programming streamers on Twitch a couple of years ago, but it was very much a kind of niche minority thing, and now it's really exploded. So that's really good. So I have a Discord. I'll just post an invite to my Discord in chat if you'd like to pop over to Discord, and you'd be very welcome. We can chat off stream, and if you've got any questions about any kind of content, or if you're looking for any kind of informal advice, I'm not qualified to give you careers advice and all that, but I can give you the benefit of any experience that I might have on becoming a developer, what it's like being a developer, becoming a development manager, and the kind of things you might face doing that. I'm also a space nut. So we do have some kind of space content, especially I'm interested in SpaceX and all things to do with that company. Our bot has a launches command, !launches. If by default it will show you upcoming launch schedule for SpaceX, but we also have other launch providers which you can use in their ULA, for example, or NASA. It will tell you all those things. That shows you there's actually a launch coming up on June the 11th for RadarSat mission. So that's another thing that you can join the Discord and follow me on. So thank you everyone who's joined and followed today. I'm going to now try and find someone to raid, which may be quite hard because it's quite late. Let's go and have a look. Let's see who's available. If anyone's got any preferences who we might want to raid, then do let me know. Oh, looks like, do you think Robert Tables is? Looks like Robert Tables is available, so we'll go and raid him, I think. So do stay on the stream, and we'll be transferring you to Robert Tables. I do appreciate everyone who's watched over this quite challenging stream, so thank you and good night, and enjoy the raid. Thanks, guys.